Hey guys, so in this video I'm going to do some trig substitution examples that are maybe like a little more complicated or they look like they could be more complicated. So I just wanted to go through these three examples and yeah, let's just get right to it. You can pause the video if you want to read them over. So this first one's interesting to me. I think this one's looks mighty complicated because when you first look at it, it doesn't even look like a trig substitution problem. So the thing that makes this a trig substitution problem is that, like, as this is like one of those cases where I probably technically could use, I could try some other techniques. Like, I cannot easily use, say, like, use substitution right out. It would require just some other, like, manipulation. So this is like a case where there's other things that you could technically try. Now, what I'm going to do, which will reveal why we need the trig substitution, is I'm going to start by multiplying by the conjugate of the denominator. And so in doing that, so what's that going to give me now? So in the denominator, I'll have 1 minus, so actually maybe I'll break this out just to make this clear. Okay, so first of all, a property of, let's write this as 1 plus x, not x plus 1. Okay, so one of the properties of square roots is that you can break them up from being 1 into just these two pieces like you see here. So what I'm going to do is I'm going to multiply the top and bottom both by the same square root, and then that doesn't change the value of the problem. And then from there, so since I'm multiplying by square roots, so just as a reminder of how square roots work, so now I've got this situation here. So this becomes now 1 minus x, 1 plus x dx. So here's like the algebra of what's going on if you weren't sure. So I'll clear some space. Okay, so now when I go through and do all this, so I've got 1 plus x squared. I don't even have to FOIL it out. I just have 1 plus x squared, the square root of 1 plus x squared. And then here I've got 1 minus x squared. So all of this will simplify then to 1 plus x over the square root of 1 minus x squared. And now we can visualize, or we can see where I would want to get my substitution in, or my trig substitution. Now, this is a video on trig substitution. I think there are other things that you could play around with. It's not like you have to use trig substitution. I think there are some other alternatives. Like, I think you could break this into two separate fractions if you wanted. But this is a video on trig substitution, so I'm going to do this using trig substitution. All right, so let's clear some space. Okay, so now I can use my little handy dandy chart. So I'm a big fan of just stating that these are the most efficient ways to kind of do your substitutions. There's a couple different ways you could approach trig substitution. I think that I like this. I think this is worthwhile to memorize just because it's the most efficient types of substitution that you'll make. There's other approaches. Some of them are not as efficient. So my x in this case then, so I'm using this 1 minus x squared, so this form here, my x will be just equal to sine theta. Therefore, my dx will be cosine theta d theta. So then I can make some substitutions. So this will be 1 plus sine theta on top, and then this will be 1 minus sine squared theta, all of this times cosine theta d theta. Okay, so let's keep going. So now I've got 1 plus sine theta, and now 1 minus sine squared theta we know is cosine squared theta, and then this is of course times cosine theta d theta. And so hopefully you can see now, right, the square root of this cosine squared, this is just cosine. So I'm just going to go ahead and cancel these out. And so look at what a nice problem we're left with. Just 1 plus sine theta d theta. Excellent. So now I will clear a little space and we'll integrate. So this will be theta minus cosine theta plus c. Okay, now from here I need to draw my reference triangle. So I'm going to use my original substitution. So let's view this as sine theta equals x over 1. So if you remember your good old SOHCAHTOA, so sine is opposite over hypotenuse. So I'm going to draw my little triangle here. Here's my opposite, here's my hypotenuse, and then here's going to be the other side. You could just figure that out using the Pythagorean theorem. Okay, so theta, then, if I look at this, theta is found by, to solve for theta, I just take inverse sine. So this will be inverse sine theta. And then cosine theta, so cosine theta is going to be the adjacent over the hypotenuse. So this will just end up being minus the square root of 1 minus x squared plus c. And there you go. So is that easier than some of the other routes that you would have taken? That's like totally a subjective thing. I think that this is straightforward for this type of problem. Yeah, I don't know. I mean, it's totally subjective. So let's take a look at another one. Okay, so moving on to the next one. So now I've got 1 over x squared minus 4 to the 3 halves. So referencing my little handy chart. So I have x squared minus 4, so that's following this form here. So I have a 4 here, so that means that my a is equal to 2, so my x will be 2 secant theta. X equals 2 secant theta. Therefore, my dx will be 2 secant theta tangent theta d theta. And so now let's just get right to it, huh? So this is going to leave me with 4 secant squared theta minus 4, all of that to the 3 halves, times 2 secant theta tangent theta d theta. And so now, so let's see. So now I can take, this will be 2 secant squared theta minus 1 to the 3 halves. And let's see, I'll write just this other stuff on top. 2 secant theta tangent theta d theta. And, oops, sorry, I wrote 4, or 2 here. I should have written 4, my bad. Okay, so now I've got 2 secant theta tangent theta. So the thing about this, the reason I like this little chart, by the way, is I've got the reminders of what identities you want to use. So secant squared theta minus 1 will equal tangent squared theta. So now I've got 4 tangent squared theta to the 3 halves. Okay, now before I go any farther, I want to do something just a little clever with this, okay? So the clever thing, I want to just think of 4. I'm going to think of 4 as 2 squared for a second, okay? So why would I do that? Well, this exponent I'm going to apply by multiplication to both exponents. So think about taking 2 times 3 halves. What happens when I multiply 2 times 3 halves? The 2's drop out. So that's going to inform how we actually simplify this thing. So I'll clear some space. Okay, so I've done nothing to the top. Secant theta tangent theta. I'll just put the d theta here. Okay, so now instead of this being, this is 2 squared times 3 halves, this will become 2 to the 3rd and then tangent to the 3rd. So you see how that's kind of like a clever trick? So now I can make some cancellations, right? So I can cancel this 2 out. I can subtract 1 from this exponent here and 1 from this exponent here, so I can cancel out those tangents. So what am I left with? Now I've got secant theta d theta over 2 squared, which is 4, tangent squared theta. All right. So now, what's next? So now we just kind of have to get a little creative with like, how are we actually going to integrate this? And so I have like a few options, but when I think through things, so like me changing this back to secant squared theta minus 1 isn't going to help with like simplifying this. There's not like an easy substitution. So when this happens, I think it's just good then to get down into the sine and cosine functions. So let me clear some space. So let's just rewrite this for a second. So secant theta is 1 over cosine theta. let's bring the 1 over 4 out here, okay? And then I've got 1 over, so tangent squared theta. So just think about what that is. So tangent is sine of theta over cosine theta, all of that squared. And then, so I've got 1 divided by all this, so I'm going to take the reciprocal. So I just like to write everything out in all these little details because it seems really simple, but like if you do too much too fast in your head, right, you're probably going to make a mistake. Like it seems like it's maybe simple, but like I think when you actually write it out, you see how not simple it is, I guess is what I'm trying to say. So more detail the better when you're writing stuff out. This cosine will cancel out. And so now I can actually see where to go with this. So let me clear some space. And let's see, so now I've got 1 over 4 cosine theta d theta over sine squared theta. All right, and you have a few options now of how to handle this. To me, the first thing that I see is to use u substitution. So I'm going to let my u be sine theta and my du be cosine theta d theta. So then I'm left with, what is this, du over u squared. And then when I integrate that, what am I left with? I've got 1/4 times negative 1 over 1 u to the negative first. Yeah, plus c. Okay, so let's clear some space. And so now I've got 1/4. Okay, so I erased what my original u was, but let's see, this is now negative 1 over 4. So my u was originally sine of theta, so this is now going to be, let's see, let's write this as 1 over 4 sine theta, there we go, plus c. Okay, so now we have to replace sine theta with the actual value. Now I have to remember, oh yeah, I come back here to my original substitution. So I'm going to review this as secant theta equals x over 2. Now the things to remember, secant theta is 1 over cosine theta. Cosine theta is typically, so you think of your SOHCAHTOA, so this will be adjacent over hypotenuse. So therefore, my secant theta, this is hypotenuse over adjacent. So don't be afraid to like write that stuff out. I feel like after you do that for a while, you kind of just remember that off the top of your head. Or you don't, and you just have to think about it every single time, you know, whatever. Whatever gets you through. So this is my hypotenuse, this is my adjacent, and so then this is going to be, let's see, what is this going to be? 4 minus x squared. Okay. So sine is opposite over adjacent. So see, I'm going to bring this negative 1 over 4 over here for a second. So if this is 1 over sine, which is normally opposite over adjacent, all right. There's a couple ways you can do this. I'll just show you if I want to keep everything in terms of sine. If you thought about this in a slightly different way, that's totally fine. So here's my opposite, 4 minus x squared over, did I say adjacent? I meant hypotenuse. Okay, so now let me rewrite this as negative x over 4 square root of 4 minus x squared, and then plus c. All right. And now for the last one. So I've got 6 over 4x squared plus 1 squared. Okay, so in this case, so I know I'm, oops, sorry, my bad. So I know I'm going to use my trig substitution, right? So if I refer to this handy dandy chart, so I've got something a little different from what I had before. So I've got a plus x squared, and I guess I just want you to appreciate that this is 4x squared plus 1. Okay. So let's just think about this logically for a second. So I have a squared plus x squared means that x equals a tangent theta. But in this case, I have, let's see, we'll write this as 1 plus 4x squared. Okay, so first of all, what's in the a position? It's just 1, okay? Now, here's how I think through this. I take the square root of x, right, and put an x here. So if I take the square root of what I've actually been given, this is going to be 2x equals that, right? Because the square root of 4 is 2, and so I take the square root of this. So 2x equals this, which means that x is going to equal 1/2 tangent theta. So I'll just write that up at the top there. So there's the substitution that I want to make. So that's kind of what makes this problem a little more complicated. So I'll clear some space. And then take the derivative. So this will be 1/2 secant squared theta d theta. Now, if you're playing along at home here, I strongly recommend that you give this video, the rest of this, a try. Hit play when you're ready, and I'll be here to show you the rest of the solution. All right, so let's just bring the 6 out. And let's see, this will be 1/2 secant squared theta d theta. And then in the bottom here, so now I have 4, so my x is 1/2 tangent theta squared, all of this, plus 1 squared. Okay, so it's kind of messing with my head a little bit, but we'll just keep pressing on. So this 1/2 we can bring out in front and divide the 6 by 2. So now I've got 3 here, secant squared theta d theta. Okay, so 1/2 squared is 4, so now I've got 4/4 tangent squared theta plus 1. So the 4's just drop out. Okay, and so now kind of messes with our minds for a second, but I'm just left with tangent squared theta plus 1. And so this is also kind of interesting. So you know, now that we've kind of reduced all of this, now I can just go ahead and use my identity. So I didn't have to do anything special with it. I didn't have to, you know, factor anything out. I actually just ended up getting to use my identity as is. So this tangent squared theta plus 1, this is just going to equal secant squared theta, and then all of that squared. And so now I can rewrite this as, let's see, I'll just continue on over here. So I'll write the 3 out here. So I've got secant squared theta, secant 4th theta, d theta. So then this becomes 1 secant squared theta, d theta. And I know that 1 secant squared theta is equal to just cosine squared theta. And so now we can use our old buddy. This is my list of helpful identities. I think these are really helpful to have memorized. So this guy right here, we're just going to plug this in. So let me clear a little space. All right, so let's see. This will be 1 plus cosine 2 theta over 2 d theta. Okay, so now I'm going to factor this 1/2 out, so I'm just left with 1 plus cosine 2 theta d theta. And now I can integrate. Let's see, I need some space. So now I get theta plus 1/2 sine 2 theta plus c. Now, the thing about this problem as you move forward in this, you know that you're going to have to make a reference triangle. And so there is a property with just trig identities that is helpful to remember at this point. And that is that cosine of 2 theta is going to be equal to 2 sine theta cosine theta. This is something that you are going to use from time to time. So then what happens as a consequence of that are those 2's, the 2 and the 1/2 cancel out. So I'm going to rewrite this then as theta and then sine theta cosine theta. Okay, so from here, let's clear some space again. And we go back to our original substitution. So I'm going to rewrite this now as tangent theta equals 2x, and I'm going to put this as 2x over 1. So I multiply both sides by 2. So this is going to help me set up my reference triangle. So my reference triangle, so I've got this, here's my theta. So I've got my SOHCAHTOA. So this is going to be opposite over adjacent. So this is 1, this is 2x, and then this will be 1 plus the square root of 1 plus 4x squared. Okay. And okay, so now to get my theta, so I have to solve this. So I just take inverse tangent. So this will be 3 over 2 inverse tangent of 2x. And then sine theta, cosine theta. So sine theta, so that's going to be opposite over hypotenuse. So that's going to be 2x over the square root of 1 plus 4x squared. And then cosine theta is going to be 1 over square root of 1 plus 4x squared. And let's see, running out of room here, but now we can simplify this whole thing. So this will turn into 3 over 2 inverse tangent 2x plus, let's see, when I multiply this 3 halves times 2x, the 2's will drop out, so this just becomes 3x on top, 1 plus 4x squared, and then all of that plus c. And so that will be the final answer. Okay, and so hopefully that gives you a pretty good breadth of some of the more just like complicated, like funny little things that can happen with some of these trig substitution problems. If you found that helpful, please consider giving the video a like. I will talk to you guys in another video. Thanks for watching.